Hello, everyone. Thank you for joining us this afternoon. My name is Antonio Mejia, and I am the team leader for Vanguard from the University of Texas at Tyler Houston Engineering Center. On the team with me are Monica Moncondui, our co-leader, Zachary Butterfrost, our communications officer, and our designers, Michael Myra and Amin Marashi. Together, we're working on the Lunar Surface Extravehicular Activity Operations Spacesuit Attachment Quick Release System. We are under the advisorship of Professor Aus Al-Shalash, and then we're working in tandem with our partners from NASA Johnson Space Center EC Group. I will pass the ball over to Michael Myra, who will tell you a little bit more about why we are here today.
Thank you, Antonio. Now our concept statement. To design two interlocking components with a quick release for a spacesuit utility belt that secures tools required by astronauts on spacewalks. Now, throughout the presentation, orange will refer to the male end and blue for the female end. Applying a quick release attachment for an astronaut to connect and disconnect their tools quickly, smoothly, and repetitive will increase the efficiency of a spacewalk. Now, here is a picture of a spacesuit and the location of where the utility belt will be located. Here is our presentation layout. Each section discussed is identified by a color marker. Background information. The Artemis program will be sending the first woman and next man to the moon in 2024. The astronauts will be landing on the South Pole region of the moon, where they will be mining for ice. Now I will pass it off to Monica to discuss the specifications.
Thank you, Michael. We broke our design specifications into 3 different categories. Starting with what you see on your screen is quantitative, then we'll look at qualitative, and finish up with safety. For the quantitative you see on your screen, the 3 I would like to point out is our assembly volume of maximum 48 inches, assembly weight of maximum of 2 pounds, and the actuation stability of minimum of 6 pounds. You see there's a strong focus on making it as small as possible, but also something that won't be activated too easily. The qualitative design specifications are a little bit more intangible. They focus mostly on the operations of the tool itself. We want the astronauts to be able to reach behind them without looking, disconnect the tool, and be able to use it without any worries of lunar dust or limited dexterity. Safety design specifications are of the utmost importance. You'll notice we focused on minimizing sharp edges and pinch points, as well as eliminating any possible spots for entrapment of fingers. You'll see how these design specifications came into play as Zachary walks us through our concept.
Thank you, Monica. Here we have our Vanguard XCMU quick release and catch system. The animation on the right shows the motion of the mechanism. The male end, displayed in orange, is attached to the tool and will slide down into the channel of the female end, displayed in blue, which is attached to the utility belt. As the male end meets the rollers, they will push apart and reform around it with the help of 2 torsion springs, securing it in place. Here we have the exploded view for our quick release assembly. Starting from the tool side on the left to the belt side on the right, we have the male end, 4 number 10 screws which secure it to the tool, 4 number 2 screws which secure the cover plate itself, the double roller catch with its 2 torsion springs, 4 number 10 screws to secure the female end to the belt, and the female end itself. The double roller catch subassembly inserts into the bottom of the female end and is then secured by sealing the cover plate onto the opening. This will help to prevent dust from reaching the latching mechanism and ensures that it is stationary. Here we can see the latch with its springs. As the male end pushes down on the rollers, they will separate, and as it moves past, they will then reform from the force of the springs in compression. A finite element analysis was performed on the areas of the 2 parts under the greatest load. As anticipated, the weakest part was the cylindrical rod on the male end, which started to permanently deform under a maximum load of about 47 pounds. This gives our device a current safety factor of 3.14 based on the male end maximum load and the 15-pound minimum load requirement. With that, I will hand it off to Amin so he can discuss the requirement compliance matrix.
Thanks, Zachary. Here we have the requirement compliance matrix for this concept design. The quantitative requirements are easier to measure compared to the qualitative ones. Our design is able to support at least 15 pounds and it fits within the specified volume. The design only uses manual power and it weighs less than 2 pounds. This design should be operable outside of the astronaut's line of sight, and it should be able to function when it's fully submerged in moon dust simulant. To test if our design is dust tolerant, the team intends to use flour and sand as substitutes for moon dust. Another important requirement is that the two pieces should mate together with little force and they should stay in place while the astronaut is walking or bending. Also, this design should be operable with EVA glove hands, which will be tested during the prototyping phase. This design should not have holes or openings that could entrap fingers, and that will also be tested during the prototyping phase. Now I'm going to hand it over to Antonio, who will explain more about our budget plans and prototyping process.
Thanks, Amin. In order to develop a comprehensive budget, the team needed to consider a couple of key elements. Things like the manufacturing cost, or the total amount of labor hours involved in machining a given part. In addition to this, we also need to have in mind the cost of materials like aluminum, stainless steel, and Teflon, which are considered in scope for the design, but things that are considered out of scope as well, as they fit within the 3D printing prototyping phase. Things like the cost of polylactic acid. And so what is shown is the total cost per unit kilogram of these materials. External to these materials, we also have certain mechanisms or certain elements in our design, things like steel torsion springs or perhaps compression springs, and so the cost of those need to also be considered. After printing one of our prototypes, we used the total mass of PLA that was utilized in order to price out the total cost. And so what is presented here is a minimum cost of $13.76 for printing of a single prototype. All of our prototypes have been produced on a Dremel Digilab 3D45 printer, which can handle various polymers, including polylactic acid, ABS, PETG, and nylon. Using the 3D printer gives us a degree of flexibility in order to confirm our system's functionality and to ensure that all of the mating or moving elements properly fit. Should the team identify design weaknesses, we're also able to pivot relatively quickly into redesign mode and re-prototyping mode to make sure that our new solution fits within the design framework. On the following slide, you see several images of the various components of our design that have been produced using a 3D printer, including the catching mechanism, the female attachment, and the overall full assembly. In terms of manufacturing, we'll likely implement a couple of different techniques, such as laser cutting, machining, lathing, sheet metal forming, and welding, as well as sourcing some materials on the open market, things like springs, tubing, or rod to make the connectors. To protect all of these pieces, we also intend to apply a surface treatment of Teflon to all of our moving parts to preserve the overall lifetime of the system, as well as to reduce friction and to mitigate dust accumulation. Recently, the team completed its first of several outreach activities with a service project at the Armand Bayou Nature Center, a nonprofit organization in the Clear Lake area. The Nature Center promotes STEM education with a focus on earth sciences, and to support the Armand Bayou Eco Explorers program, the team took on the challenge of restoring a rundown footbridge which connects the center to a wildlife observation platform. We were involved in every single stage of the process, including safety training, planning, drafting, measuring, demolition, and construction. Together, we were able to learn more about working as a team and put to practice our much valued engineering education. Next, we plan to participate in the Prairie Pandemonium, a replanting and sustainability project to aid in maintaining the natural ecosystem of the area.
Our current outreach plan includes 5 events, starting with this semester and going throughout the spring 2021 semester. We look forward for the opportunity to engage more with our local communities and schools. The Vanguard team from University of Texas at Tyler would like to thank you for your time and listening to our presentation. We welcome any questions or comments you may now have.